Hey
Yeah.
Gil, welcome back.
Hey, thanks for having me again. Um,
Yeah,
I just listened through the recording that you posted on our previous session, and it was fun
and you
to
like
hear.
that the conversation?
Yeah,
Uh,
definitely.
and
Hmm.
uh, and the cliffhanger was for me a big one because I was fascinated by the chip, and I also found it on Wikipedia. So there's a picture of the chip. So what was it? Is it? Was it like Intel based, ARM based? You implemented it from scratch, or designed it from scratch? How it happened? And who gets an idea to create a Java chip, right? So this is incredible. So I was completely fascinated by it. So I have to know it.
Yeah. So, so the chip you're talking about is called Vega.
Hmm.
Yeah, you could probably find interesting things about it on Google and Wikipedia. And it is an Azul specific chip that we got to build three generations of: a Vega 1, a Vega 2, and a Vega 3,
Hmm.
starting from the early to the late 2000s.
Hmm.
Azul transitioned to being a software only company after that. Vega 3 was the last generation of the chip and the machines that were built on it. But that chip had some really interesting things in it, and some things that I think actually moved the industry forward. Yes, in general,
Hmm.
we see some of the things that we had innovated and started for the first time there showing up in the regular way servers are run
Hmm.
today, a decade and a half or more later.
Hmm.
Um, and that's a good thing. Um, you asked about, was it built on Intel or other things? No, it was our own instruction set.
Hmm.
And the machines that was running, that it was built to run on, were our own machines. The OS kernel that ran on those chips and ran those machines was our own OS kernel, and the JVM that ran on top of that with some very interesting proxying or virtualization technology that we talked about some in the
Hmm.
last session was our own JVM. Although that JVM was certainly built based on the Sun Java SE license technology at the time in the early 2000s, what later became the core of OpenJDK a decade
Hmm.
or so later. Um, so we did a lot, and this started around, well, it started in 2002. Um, but we put together an amazing team of engineers, of technical people. It was one of those examples of probably a thing you can only ever do in Silicon Valley, because getting the right set of people under one roof was really hard to do anywhere else. Would have been hard to do anywhere else. These days, with Zoom and Google Meets and other things, it may have been easier. But back in the 2000s, you pretty much had to be in a building together to do this kind of stuff.
Hmm.
And we got hardware folks, chip design folks, architects, actual chip, um, the entire team to build it, a full, impressive chip out, as well as the various stack levels of software people in and well one building, including OS kernel people, device drivers, I/O, etc. Um, General application programmers, including for management systems and other things that would manage large resources. Very focused Java virtual machine capabilities, both from just an ability to get it done, get it working, get it reliable, and all the way to architecting and finding great new opportunities for optimization, for breakthroughs in new ways of doing things that could solve real problems for Java. And it's probably one of the most fun times I've had ever
But
building.
this is the what interests me right now. I think this is the only example in the history that company does everything from scratch. Right? Apple would be kind of, but there is not a lot of company which design the hardware, the operating system, and the entire software, the entire stack. Right?
I
Cisco
don't think
maybe.
that's quite true. That's actually, it's rare today, but you could think of it as maybe we were one of the last. Sun
Hmm.
Sun did all this, right? Um, so did companies like Pyramid and
Okay.
SGI.
Hmm.
Um, and various others. There was definitely an evolution towards chips being made separately from the full stack that goes with it. But the origin was actually chips, operating system, and software done by one company. And we really evolved to chips are made by one company. In fact, chips are designed by one company, manufactured by another company, is the state, right?
Right.
And then physical machines made out of those chips made by a company, but somebody else makes the operating system, somebody else makes the software, goes on top of them, and companies specialize. That's not what the world looked like when we started. And like I said, I don't think we see that shape anymore. That's not a bad thing. It actually means that we get to move quicker in the world today. But back in the 2000s, x86 was a toy. x86 was this thing that ran in PCs, and people did put PCs in racks and called them servers. But if you look at the architecture at the time, and all the way to about 2009, an x86 server had the architecture of a desktop PC. It had a front-side bus. It had a single memory controller. If it could do 4 CPUs, that was a big number. And it was highly limited in its I/O architecture and other things too. It was rare to find ECC memory, all kinds of stuff like that. Were not, PCs. x86 came from the low-end client world. Servers with their heft and robustness and seriousness were made by companies that did vertical stuff, by Sun, by IBM, by SGI, by HP, and various other companies that probably, I don't want to leave anybody else out, but in each one of those cases, you had pretty strong vertical integration. The thing we were aiming to do is to build a vertically integrated hardware product with the software that is focused on using what that product would do, but not try and get people to build software for our systems. We built a piece of hardware and a layer of software that would be able to run the vast majority of Java applications completely unchanged without even people knowing. And that was, we virtualized Java, or we used Java as a mount point and virtualization point to achieve this, so that regular operating systems and computers, whether they're Linux on x86 or Sun OS on Spark or HPPA on Itanium and HPPA with HPUX, AIX, ZLinux, any of those could actually use what we had without changing anything, simply by virtualizing the JVM. And to us, what we were building was a basically mountable compute power. CPU and memory hooked up through a JVM proxy, what we today would call a virtualized JVM, to deliver capacity into a Java application, into environments where the vast majority of capacity was being consumed by a Java application. So the transparency layer is what allowed us to say, we will build this, but other people will use it without changing their software. But the back ends, we built them in the way people built machines. And we found what we would today call a good excuse, but we think was a good reason, to design a lot of things that from scratch. Now, we didn't.
But one question: I think it seems like to me now that you were forced to build your own chip, right? Because you couldn't just pick anything which was good enough. So I mean, you couldn't pick the Sun chip because it was a different company, and Intel was a toy. AMD was similar to Intel, right? It was a little bit better, but not significantly better.
Embedded systems at the time, etc. MIPS wasn't really viable for us. Look, we definitely, in every layer of the stack, we did a build versus buy or build versus leverage decision. And we chose to build our own chip. We chose to build our own kernel. We chose to build our own I/O layers. Not because we wanted to invent new things necessarily. It was certainly fun to do them. It's because there was nothing for us to leverage. And one of the things we could talk about maybe is some interesting architectural necessities that made it so.
Yeah.
Let's take the chip. Why do we need to build our own instruction set, for example? Or why do we need to build our own chip to begin with? The problem we're aiming to solve is large mountable compute power. we wanted hundreds of cores, hundreds of gigabytes that would be shareable by tens or hundreds of servers.
Mm-hmm.
That's like disk systems or routers we were thinking at that scale. And that meant we needed to pack hundreds of CPU cores into a box. We also needed them to be fully coherent and symmetric. I'm still a big believer of effective symmetric multiprocessing, meaning architectures where, and this was always an interesting philosophical debate within Azul, but architectures that have inherent strong NUMA behaviors, non-uniform in the sense that memory that's far or near has dramatic performance differences, not a little bit of noise, but you just can't access that nearly as much as this, to the level that you force software to work with that, generally end up with very specialized software. It's not that those systems don't exist. They exist in hordes. They existed in hordes. And as I said, I came from the network processing world where that works great. Packet processing is a very laterally scalable thing. But in a world where you want to run unmodified software is built to run on a symmetric multiprocessor, period.
Mm-hmm. Mm-hmm.
There is no magic way to take that and transition it to a highly NUMA architecture where memory that is far is 1/10 the bandwidth and 100 times the latency. You can't, that just doesn't work in scale. So we said we need a symmetric multiprocessor with hundreds of CPUs. If you looked at who was building things that were not quite the size we wanted, but approaching it, it was companies like Sun, IBM, HP, SGI, right? Those packed hundreds of CPUs into one, smaller than we wanted, but still they had that. But as you said, each one of those was proprietary. The companies were not selling the chips to build those systems from. They were building the systems with their own chips.
Mm-hmm.
So if we wanted a system, we had to build a chip that was able to do that.
And which you build a chip? So which specs the chip had? How many cores it had, or what was the speed? And yeah.
So we have Vega 1 through Vega 3, so we can either start at the beginning or at the end.
Beginning, of course.
So the very first Vega 1, had 24 CPU cores per chip, which today sounds meh, but for a chip that actually came out in 2004, that was the biggest number of cores you had in any chip anywhere in the world ever.
It sounds even today impressive, I have to say.
Yeah. So, well, I mean, a lot of chips have 24 or more, right? I mean,
but I mean, it was 20 years ago, right?
Yep. Yeah, almost exactly. So 24 CPUs. We quickly evolved that to 48 and then to 54 through Vega 2 and Vega 3. Similar architecture. Each of those cores was a classic RISC CPU with some interesting capabilities, but a RISC CPU. Mm-hmm. This was not a Java bytecode processor. This was not a stack machine. We had people that understood that those are silly things to build when you have a JIT compiler. Mm-hmm. We built them to run code, and to run code that what we believed was code coming out of Java JITs in a good, effective way, helping the JIT, giving it tools, and helping the JVM, giving it tools to solve the hard things that make JVM designers go crazy about current chips, but that's not the instruction set itself, really. Mm-hmm. There's some of the instruction set, but not all. So each CPU was a CPU. It was a throughput machine in the sense that we were not aiming to be really, really fast in one thread. We were aiming to have tons of capacity, ability to run laterally scalable within an SMP. So you would call this vertical scaling, but laterally scale across threads very effectively. So that Java would be able to use tens of threads, really, not just sort of, concurrently on actual CPUs that would work, and share the memory very effectively. Mm-hmm. And so we were probably at about a third of the power per CPU that powerful servers had, or x86 had. Mm-hmm. But we had hundreds of them. And if you think about the problem space we were aiming at, we weren't trying to figure out how to run one thing really quickly. We were trying to figure out how to power things that had natural parallelism in their business logic.
Mm-hmm.
The business logic problem of an application server is not how to do one operation quickly. It's how to do 1,000 different operations that have nothing to do with each other
Mm-hmm.
at a certain throughput with good enough response times for each. So
Mm-hmm.
you get a benefit for doing more, not for doing each one quicker.
Mm-hmm.
Now, they need to be done in time. They can't be outrageously slow. But, once you load it up, the fact that we could do 20 times as much in one machine means that the speed of individuals is better than the speed of a fast CPU that can only do one of them at a time.
So it was like 200 megahertz, or?
No, it was a gigahertz plus in those
Wow.
things. But that's at a time where x86 were running 3 gigahertz, right? So
yeah, it was what?
It was also a RISC machine, but it was not a highly superscalar one.
Mm-hmm.
It was to some degree, but it wasn't like highly complicated. It was not an out of order engine. There are a lot of things that were simpler about the RISC machine that we built. But we fed it in all kinds of ways that made it very effective, without needing the generic high parallelism within the chip. So let me give you some simple examples of architectural choices we made on the chip level that matched things that JVMs do a lot, or in general that process the things with a lot of software stack stuff do a lot. Our chip had a hardware managed register window. We weren't the first to do this. Spark had those. Itinium had it to some degree. Other CPUs had too. But the chip was designed specifically, the instruction set was designed specifically so that when you make a call, a function call, method call, whatever, a call, you could designate which of your registers becomes register 0 of the callee, shifting, and the hardware shifts the stack under you. So from that point on, the registers are effectively renumbered. But this does not happen at a fixed granularity. For example, in Spark, that's done 8 registers at a time. Your input becomes the output, your output becomes the input, the output is new, the generals are 8. This was just the window shifts. Your R7 may become R0. When you pop, it comes back, etc. And hardware is pretty good at that's something hardware can do very well. Now, the hardware in the background managed the entire spill-fill window. So the hardware could spill and fill registers to actual stack memory on its own, not as a specific set of instructions that needs to be run in parallel, but simply because the hardware knows how to manage the register stack. So rather than this being a generic parallel operation, the hardware could background manage this. Now, the reason this fits in very nicely is because those kind of jumps happen quite a bit. They're very convenient to do this way. It avoids the need to have spilling and filling instructions around method calls. So we eliminate a tremendous number of instructions in doing this, as long as we can fit things in registers pretty well. But let's go a step beyond that. A very common operation that ends up happening in JITted code is that you jump to a method speculating that the type of the object that you have is a specific type that you're jumping to the method of. This is generally called monomorphic inline caching or monomorphic speculative calls. So the world you have is polymorphic. There could be 10 possible implementers, possible receivers, but you believe that you are jumping to one of a specific type. Because you're running in the dog kennel, and for some reason, the only thing that ever appears as dogs, so we're speculating we're only going to see dogs, and we're going to jump there. Now, to manage that kind of stuff in a regular CPU, you have to, follow the object pointer, find the type, compare the type to this constant type you expect, jump somewhere if you don't like it, and then do the call if you do. There's a bunch of instructions I just described. In Vega, this was all one call instruction that did everything. One ISC instruction that achieved the entire set of sequences there. Why? Well, Vega pointers had types. The top bits of the pointers were not address, they were class IDs. Vega calls one of the call instructions had an expected type. And R0 in a virtual method call is always your object.
Mm-hmm.
Like the first parameter is the object. So the register I'm telling you to make R0 of your callee is also a register containing a pointer to the object. That pointer in its stop bits has a type, and the call has a constant ID to compare that type to. And the hardware will do all that, call through, but if the type doesn't match the expected one, it will trap. To a user mode managed exception, it will handle that.
So Vega was kind of optimized what JIT does, but it didn't run, of course, the bytecode, nothing. It just knew that the specific operations are more common in JITted code, and you just optimize the hardware for it, right?
Yep, you could say that we optimized for guarded speculative type calls.
Mm-hmm.
We had a single RISC instruction that performed what normally would need 10 other instructions and an extra memory access to achieve. But we did it in one instruction simply, not because the hardware was somehow complicated. This is very easy stuff for hardware to achieve. Just a bunch of bit comparisons and conditional traps and that kind of stuff.
Okay.
Hardware's good at that.
How many chips you had in one enclosure or in one server?
So Vega scaled up to 16 fully symmetric chips. Each with, it started with 24 cores in the Vega 1, 54 cores by Vega 3. So at the biggest, it was 864 CPUs fully symmetrically meshed. Now, when I say fully symmetrically, each chip had 15 connections to other chips, chip-to-chip connections.
Mm-hmm.
And those connections were used for coherency and memory traffic and everything. There were high-speed serial links. The cool thing about this is they were all, like the chips had direct connections, like a chip and another chip, just copper wire between them. If you drew this, you had that classic circle of 16 things with every possible line interconnecting a full mesh kind of circle. Mm-hmm. And in hardware implementation, this was a very thick, multi-layered backplane that was plain copper and just passive. Mm-hmm. Like there were no transistors on it, right? It's just wires that go from board to board in all the mesh. It was very, very thick, very heavy. I have one in my garage. But it was just all copper, right? Mm-hmm. I mean, lots and lots of copper wires. I think it amounted to, well, over 2,000 copper wires routed in different ways. But again,
crazy. So this manufacturing was also challenging, I think, right, of the thing.
No, this was actually pretty well doable and normal, not even challenging state-of-the-art stuff. We didn't go and do exotic manufacturing things, but we did try to keep things simple wherever we could. So I'll give you an example on an architecture level for the chip. We're building for a symmetric multiprocessor. And the assumption was if I'm one CPU, the memory I want to access could be anywhere in the system. There's no such thing as I know how to put my core next to the memory that's interested. Things move around way too quick. When I context switched out, I could have been in another part of the system. I don't want to depend strongly on affinity for something I did a second ago, that kind of stuff. What that means is if you're on one chip, the chance of your memory being not connected to your chip, because each chip had its own local memory controllers, because that's how we had 64 memory controllers across the system of 16 chips. The chance of you actually having your memory be close to you was only 1 in 16, right? So there's 1 in 16 chance it's close, which is pretty much you're not going to be lucky, right? Mm-hmm. So instead of trying to put things near you and try to optimize that, we did the exact opposite. We actually striped our memory across the system by cache line, not by page. So a single object could have been striped across 5 memory controllers, some of them on different chips, because each cache line ended up somewhere else in the system to get an even spread, to get a statistically even spread, the opposite of trying to create over affinity. Now, a side effect of this was, since the likelihood of using the local memory controller for performance optimized stuff is very low, there's no point in trying to optimize the local path from a CPU to the memory that's attached to its chip. Most of your access will be your CPU leaving the chip, going to another chip, looking at its memory controller, coming back. Mm-hmm. So we had no local interconnect between CPUs and their memory controller. To talk to the memory controller on the same chip, we left the chip and came back in. because we
So
already
you
had,
assume it's always remote, right? So you assumed it's always remote?
even the local memory controller was remote. And
Yeah.
the reason that was useful is then we didn't have to build a piece of logic for that. We already had exactly the part of logic to talk to other chips to have memory control. So our chip was just as remote to ourselves from a memory perspective than other chips that it was connected to. And that simplified things. It had no ding or impact on performance because things were spread out anyway. But that's an example of an architectural choice that is driven by, we're going to build this for symmetric ladder, multi-threaded execution with assuming that things are going to leave chips. So why even try not to? What was important is you only go one hop. The CPU goes to its cache. The cache leaves the chip talking to a centralized cache domain thing on another chip that has a memory controller next to it. It passes back and responds. That's one hop and back. There were no multi-hop situations anywhere in the system. There were no situations where to get to some memory, you went through one chip to another chip to another chip. It was your CPU to your cache across a chip-to-chip interconnect to a memory controller and a coherency domain and back, and that's it. Flat.
But the memory controller had to know where the data lives, right? So there was some kind of hashing or whatever, so that okay, this piece of thing is on this chip, right?
Well, each memory controller was only responsible for its addresses. So memory controllers didn't have to do anything other than...
Okay, you have the memory address. So because you had the memory address, you know in which memory controller it was, right? This was the trick.
Yes, that's when I said stripe by cache line. Each cache line ended up on, if you imagine 64 stripes, each one line long. So if you walk through a 4K page in memory, you would be looking at, what is it, 2 to the 12th divided by 2 to the 5th, so 2 to the 7th, 128 different cache lines. That's 2 circles around. So 2 kilobytes linearly would be spread across the entire system, one cache at a time. Each memory controller only saw its part. Each coherency domain next to a memory controller that deals with 864-byte coherency for the cache lines associated with those addresses was only on one chip. There were 64 of those controllers spread around in a circle, each one responsible for a stripe. There is no need for any coordination between them.
You know what it reminds me of? NoSQL database design. 20 layers above. Almost very, very similar. So it was, but this was what is called consistent hashing. If you have the key, you know where it lives, and you go there and pick the data. This was also, this is actually this is why I ask you, because for me, this is actually very, very similar. It's interesting. What I also wanted to ask you is about the RAM itself, the chips. You built them as well, or were it theirs?
No, theirs was just standard DDR.
Okay, so at least something standard. There was not everything from.
I mean, we only built what we had to. We built these chips because nobody else made chips of the scale we needed. Certainly not ones they would sell.
And how much RAM you can put to the machine, to the largest one?
Vega 3 went up to 3/4 of a terabyte in 2006. So think about what that. I mean, today that's not an exotic number. Back then it was.
Yeah, and energy consumption was it like it was or heat or whatever. There was like it was comparable. I mean, comparing to Intel, it was probably cold.
It was not a super hot chip. It certainly, it was it ran hot. Memory also consumes power, but it wasn't some super challenging to cool down thing. It used very conventional heatsink technologies and regular airflows.
Okay.
Nothing exotic about that. Really good engineering went into that, obviously, but we didn't do some things that were like, we didn't need to burn too much. I'd say if you look at some other exciting architectural things, Vega had transactional memory support, hardware transactional memory support. It was the first machine to ever have hardware transactional memory support. And I think it's still the only machine that had a lasting one that was used. Intel.
How it works? So what is it?
Hardware transactional memory basically means that we could speculatively attempt to perform an atomic operation across many hardware addresses.
Oh,
We actually
okay.
called our feature SMA, speculative multi-address atomicity. That's what it. That's
Okay.
what. And now we did not invent the concept. It was evolved in academia before us, and some really cool stuff that eventually ended up in the Intel TSX designs too.
Mm-hmm.
But we were definitely the first ones to bring it to market. The SMA concept is pretty simple. It's rather than say I need to do this operation and guarantee it as its asymmetry, like a compare and swap operation or an atomic integer increment, or what you want to call those. This says I'd like to do these operations and I'm hoping they're going to be atomic, and if they're not, please cancel. And I'll deal with the cancel. So fundamentally, you start with a speculate, a bunch of operations, and a commit. There's a speculate instruction or an equivalent. There's whatever you do to memory in the middle. And there's a commit that says, if all that was achieved atomically, then we're done. And if it's not, I need you to erase everything that we just did and go back to the speculate. There's also an abort command if you really need to abort, but the hardware will automatically abort if atomicity is lost. It turns out that the ability to do that is actually really cheap to do in hardware. It's so surprisingly cheap that you wonder why people haven't done it before or still. Because existing hardware cache coherency protocols already do everything needed to achieve this. It is nearly trivial for hardware to establish this atomicity given the right semantic instructions. So we built it, we did it, and we actually did the minimal needed in hardware, leaving the rest to software. So for example, if you failed and you went back, the hardware was only responsible for getting rid of the memory state changes, but not responsible for any CPU or register cleanup. The software could save the state before the speculate, and if an abort happened, it would restore the save that it's saved, the state that is saved, much like a traditional long jump, set jump and long jump operation in low level C. So you could think of it as a set jump, speculate, and abort as a long jump back to the thing saved. But if you succeed, then you go forward. Now, what did we use this for? We used this to run Java synchronized blocks in parallel with each other. We can have 100 threads in the same synchronous block on the same monitor running in threads concurrently. And as long as they didn't actually collide in actual memory locations, modifying them in ways that somehow collided with atomicity to each other, we could blow through that. And that had some really cool effects.
One question. If you had a hash map, let's say, and hash map is a data structure and it was synchronized, but it could be spread across several memory addresses, right? So what it meant, you could still access an hash map concurrently.
Yes, that's exactly what it was for. So if you think about it, synchronized around one value, okay, there's not much we could do about that if you're going to modify the value. However, synchronized with rare writing and hot reading, we could do that. So a write would cause all the readers to fail their speculation, but readers and readers do not collide.
But it's incredible if you think about it.
If you look at a hash map, you can write in one part of the hash map, write in another part of the hash map. As long as those were different cache lines, that's not an atomicity break. So at least early on, this had some very interesting, cool effects. I did some talks at the time and since about using speculative hardware atomicity or transactional hardware memory for eliding locks in Java. And there's some interesting conclusions. This worked great for code that people never tried to improve. If it was naive code that simply had fat locks around it, this actually exposed parallelism in the code very conveniently.
But other way around, you could write simple code, synchronize it so it works correctly, and on the Vega it would be faster, right?
Yeah. Oh, it would be parallel.
Yeah.
Dramatically faster. However, it turned out that the minute people cared a little bit about the code that we're looking at and tried to do things to improve it from a concurrency point of view, the efforts that they tend to do would break the ability to speculate. is what is the first thing you do when you start studying the performance of a concurrently accessed thing with synchronization? You start counting. So invariably, the things that had any kind of studies on them put counters inside the critical code that would count this or count that or track this or track that. And the counters then become hot contention points on data that is modified, which means you have an actual modification that collides between holders of the lock. Now, the reason people do that is you're holding the lock, so you own it. Why not change things? Mm-hmm. But the fact that you do this just for instrumentation purposes tended to break the ability to speculate.
Mm-hmm. So and was a volatile a problem, or you ignored volatile?
It didn't matter.
Yeah, exactly. So you could ignore it. But what I know is on other chipsets, it is a problem. If you put volatile, it is forced, to forget the cache, right?
The ordering effects. So another interesting thing is atomicity and memory ordering are two orthogonal concepts. And they were orthogonal in Vega. In most chips, they're tied closely together. So, for example, we're used to thinking of a locked CAS in x86 as a memory ordering atomic operation. The atomicity and the memory ordering come together. In Vega, they have nothing to do with each other. Atomicity and coherency have to do with one cache line. Mm-hmm. And cache coherency protocols take care of that. Ordering is between cache lines. Mm-hmm. Now, Vega had ordering instructions that were interestingly tied to the Java memory model. We could do load, load, store, load, store, and spell out which ordering fences we wanted, but those happened as their own instructions between other instructions. No instruction had an implied order. Mm-hmm. So, for example, atomicity didn't mean ordering. Mm-hmm. You wanted atomicity with a strong order, you would do the atomic operation, then do a fence instruction that's as strong as you want, or as weak as you want, right? So that allowed us to not have to overly burden things. The other part that's important is whenever you're within a speculatively executed block, ordering doesn't matter. It's atomic across everything. So ordering operations have no meaning while you're speculating, which means volatile access is just as fast while speculating as any other access.
But you meant the term is transactional memory. It is actually optimistic, optimistic transactions. Interestingly, it is not like pessimistic that you're locking something. You're assuming it will go well, and then recover. Mm-hmm.
So speculative multi-address atomicity.
Yeah, exactly. Speculative. Okay, speculative. Yeah.
And the hardware's job is to detect and revert the changes. That's its entire job. Mm-hmm. The rest, the software will handle. If you're unlucky and your optimism didn't pay off, then you deal with it in software. Now, one of the obvious things, why can we do this well? Because the software learns. Mm-hmm. Software speculates everything, and then when things fail, you stop speculating them. Mm-hmm. So if I have a lock that keeps failing, I'm not going to keep speculating it. We'll just do the regular locking. And if I have a lock that seems to do well, then we'll speculate it. And that was done on a monitor by monitor, instance by instance basis at the JVM level. Mm-hmm. So if we could extract parallelism, we did. And if we couldn't, it didn't hurt because we would optimize, we would just compile and optimize without the speculation part for it, right? And it was fast.
Actually, incredible. So maybe last question is, what was the Sun reaction to it? Sun liked, your Vega design, or what was an interesting relation, I think, right? Because they had, interesting.
So, look, I mean, that's a question at various levels, obviously. We definitely were, if you look at the server market, we were probably seen as competitors, although we were small, they were big. So how much could you be competing? From a fame and credit point of view, we were both racing for the multi-core stuff. When we came out with our 24 chip, with a 24 CPU Vega 1, Sun had come out with their 8 CPU Niagara. Mm-hmm. When we got to 54 CPUs, I think they were at 16. Mm-hmm. So we were definitely, at the forefront of multi-core when that was a thing. we owned the front line of that. Obviously, we had the most cores and all that,
Okay.
and our design they were so vastly different that there wasn't really much there. Like Niagara was a general purpose Spark CPU with heavy symmetric multi-threading. We had a different instruction set, a different memory architecture, a different everything. So they were not similar in any real way, except for they were both multi-core at a time when multi-core was taking off. Our coherency design, our lateral SMP design, our approach to dedicated CPUs per threads at the time, and that kind of stuff were all very, very different.
Okay. So I think we don't have too much time today, so we should stop the podcast now. And I hope you could reuse lots of the hardware design to software, right? So I guess if you would take a look at the Zulu, for instance, or one of your JDKs, we will find some old concepts in software, right?
So I think there are various things, and we could talk about them next time if we want. So for example, we developed a concurrent garbage collector, and we did put in Vega things that assisted and helped with executing its fundamental operations more quickly. Specifically, we invented something called the loaded value barrier. You can find it in academic papers by Cliff and I, and later in the C4 garbage collector paper. It is a category of barrier used by concurrent collectors today. It's the same barrier that CGC and Shenandoah use today, logically. And we created it. It's got certain characteristics that make it a viable read bearing. And Vega had a way to do it in one instruction.
Okay.
Now, that's an example. But we definitely took that to regular CPUs do it too. Other interesting concepts had to do with cache line zeroing and allocation pipelines, things like that we now see in other CPUs. We could probably point to various cool things that we did there that we then took to pure software and that we see other CPUs improve on today too.
Perfect. So I would say I would like to talk now about this a bit, and of course what happens now at Azul next time, and where people can find you on the internet.
I'm various places on Twitter and Instagram. I'm at Gil Tene, Giltene. You could find me on LinkedIn. Obviously, I show up in various places, have a bunch of talks if you Google my name, and there's a mechanical sympathy Google group that I post on. Haven't in a couple of years, but I think there's some really good material there, even going several years back. You can find some deep discussions on. I also blog at Stuff Gil Says.
Stuff Gil Says. Okay.
So if you wanna find some of my reminiscing and stuff, you can look at Stuff Gil Says. And
Thank you a lot. It was a pleasure today, and now I know a little bit how Vega worked, back then.